At the deepest level of reality, the universe does not behave the way human intuition expects. What we experience as solid, continuous, and orderly dissolves into probabilities, fluctuations, and strange symmetries. Among the most unsettling discoveries in modern physics is the realization that certain particles behave as if they are moving backward in time. This idea is not a metaphor, nor a philosophical trick. It emerges directly from the mathematical structure of the laws that govern the subatomic world, and has been confirmed repeatedly by experiments with extraordinary precision. To understand why this idea shocked physicists, it helps to begin with how time appears in everyday life. Time moves in one direction, causes precede effects, a wound heals but never unhappens, smoke spreads but never gathers itself back into a cigarette. This irreversible flow is so deeply ingrained in human experience that it feels like a fundamental law of nature. Yet when physicists began probing the behavior of particles smaller than atoms, they found that this familiar arrow of time was not written into the most basic equations. In classical physics, time is a parameter that ticks forward uniformly. Newton's laws work just as well if time is reversed mathematically, but real-world processes introduce friction, heat, and disorder, which break that symmetry. In the quantum world, however, even those comforting assumptions begin to fail. When scientists developed equations to describe electrons, photons, and other fundamental particles, they noticed something disturbing. The equations did not forbid motion backward in time. In fact, they allowed it naturally. One of the earliest clues came from the equations describing relativistic particles. When quantum mechanics was combined with Einstein's special relativity, the resulting mathematics produced solutions that seemed physically impossible. Some solutions described particles with negative energy, moving backward through time. At first, these solutions were treated as meaningless artifacts of the math, something to be discarded so the theory could make sense again. But the more physicists tried to eliminate them, the more stubbornly they reappeared. Nature was giving a warning. The universe did not care whether the equations felt comfortable or intuitive. The equations worked. They predicted experimental results correctly. Ignoring parts of them simply because they seemed strange was no longer an option. As experiments grew more precise, physicists began detecting particles that seemed to defy conventional explanations. These particles had the same mass as known particles, but opposite electrical charge. They appeared suddenly in high-energy collisions, vanished upon contact with ordinary matter, and left behind pure energy. These were antiparticles, and their existence forced scientists to rethink everything they believed about time, matter, and symmetry. Antimatter was not just exotic, it was unsettling. Why should every particle have a mirror opposite? Why should the universe allow matter and antimatter to annihilate each other completely? And most importantly, what did antimatter really represent? Was it simply a new type of substance, or was it something deeper? This is where the idea of particles behaving as if they move backward in time becomes unavoidable. When physicists examined the equations more carefully, they discovered a profound equivalence. A particle with positive energy moving backward in time behaved mathematically exactly the same as a particle with opposite charge moving forward in time. There was no difference in the predictions, no difference in measurable outcomes. The universe made no distinction. This equivalence was not poetic or symbolic. It was precise. Every interaction, every scattering event, every emission of light followed the same rules under this interpretation. The math did not merely allow backward time motion. It embraced it as a natural description of reality. This realization forced a radical shift in thinking. Instead of imagining antimatter as an entirely separate category of existence, physicists could interpret it as ordinary matter traveling backward through time. When such a particle appears to us, moving forward in time, we perceive it as antimatter. When it meets matter, the interaction looks like annihilation. But from another perspective, it is a continuous process that respects the symmetry of time. The shock of this idea cannot be overstated. It challenged centuries of assumptions about causality. If particles can move backward in time, what happens to cause and effect? Does the future influence the past? Does time even exist as a fundamental entity, or is it an emergent feature of deeper laws? The answer, as physics revealed, is both humbling and unsettling. At the quantum level, time does not behave like a one-way road. The fundamental equations are largely time-symmetric. They do not care whether time flows forward or backward. The asymmetry we experience arises from large-scale effects like entropy, not from the basic laws themselves. This means that when a particle interaction is examined in isolation, reversing the direction of time produces an equally valid process. A particle emitting a photon forward in time looks mathematically identical to a particle absorbing a photon backward in time. The universe permits both descriptions, and experiments confirm that the predictions remain unchanged. One of the most compelling demonstrations of this comes from particle collision experiments. When high-energy particles collide, they produce showers of new particles and antiparticles. These events can be described using time, forward or time, reversed interpretations with equal success. The outcomes match observations regardless of which viewpoint is chosen. This is not philosophical flexibility. It is experimental fact. The idea that particles behave as if they move backward in time also explains why certain interactions appear instantaneous or non-local. In quantum processes, cause and effect can blur. Events separated by space and time influence each other in ways that defy classical explanations. When time symmetry is taken seriously, these puzzles become less mysterious. What looks like an effect preceding its cause may simply be a misinterpretation of a time-reversed process. This does not mean that macroscopic time travel is possible or that paradoxes like changing the past occur. The backward in time behavior exists within strict quantum rules. It does not allow information to be sent into the past in a way that violates consistency. The universe remains logically stable, even if its workings are deeply counterintuitive. What makes this idea so powerful is not its strangeness, but its necessity. Without allowing particles to behave as if they move backward in time, modern physics breaks down. Calculations become inconsistent. Predictions fail. Experiments no longer match theory. The backward time interpretation is not an optional curiosity. It is a structural feature of reality as described by our best theories. This realization reshaped how physicists visualize interactions. Instead of thinking only in terms of particles moving forward, they learned to see interactions as timeless processes, symmetrical in both directions. This shift led to new tools, new calculations, and new insights that transformed particle physics into a precise and predictive science. The mystery, however, remains profound. If particles can move backward in time at the quantum level, why do we never see such behavior in everyday life? Why does time feel so rigid and irreversible? The answer lies in scale. Quantum effects dominate at the smallest levels, but they average out at larger scales. The backward time behaviors cancel each other statistically, leaving behind the familiar arrow of time driven by entropy. In this sense, the flow of time is not fundamental, it is emergent. It arises from the collective behavior of countless particles, each obeying time, symmetric laws. The universe does not privilege the past over the future. It is we who do, because of how complex systems evolve. This understanding forces a reevaluation of what time actually is. Rather than a universal river carrying everything forward, time may be more like a coordinate, similar to space. Just as left and right have no inherent preference, neither may past and future at the deepest level of physics. The preference emerges only when systems become large, warm, and disordered. The idea that particles behave as if they move backward in time stands as one of the most challenging and illuminating insights in modern science. It shows that reality is not obligated to align with human intuition. It reveals a universe governed by symmetry, consistency, and mathematical elegance rather than common sense. What once seemed impossible has become unavoidable. Particles do not merely move through time, they obey laws that treat time as reversible. And in doing so, they reveal a universe far stranger, deeper, and more beautiful than any simple story of past, present, and future could ever capture. This mystery is not a failure of understanding. It is a triumph. It shows that by following evidence wherever it leads, even into the most unsettling ideas, humanity can glimpse the true structure of reality. And in that structure, time is not a one-way door, but a dimension woven into the fabric of existence itself. Richard Feynman's radical rethinking of time, matter, and antimatter did not begin as an attempt to be revolutionary. It began as an attempt to be honest with nature. Physics, at its core, is not about preserving intuition or protecting tradition. It is about describing reality as accurately as possible, even when that description feels deeply uncomfortable. Feynman understood this better than most, and it led him to one of the most daring conceptual shifts in modern science. Before Feynman, antimatter was treated as an odd mathematical consequence of quantum equations, something that existed because the math allowed it, not because physicists truly understood what it meant. The equations that combined quantum mechanics with Einstein's relativity produced strange results, including negative energies and reversed motions. Many scientists tried to patch these problems, hoping to force reality back into familiar categories. Feynman did the opposite. He asked a simple but dangerous question: what if the equations are right and our interpretation is wrong? To appreciate how radical this was, it is important to understand how deeply time is embedded in human thinking. Time defines memory, identity, and causality. Everything we know about existence is framed by the idea that the past is fixed and the future is open. Even Einstein's relativity, which altered our understanding of time, still preserved its forward flow in lived experience. Feynman, however, was willing to loosen even that anchor. When Feynman examined particle interactions, he noticed that the mathematical description did not care about the direction of time. The same interaction could be drawn with particles moving forward or backward, and the predictions remained unchanged. This was not a vague resemblance. It was exact equivalence. The universe, according to the equations, made no distinction between a particle moving forward in time and an antiparticle moving forward in time if one was instead interpreted as moving backward. This insight reframed antimatter completely. Instead of being a mysterious opposite substance, antimatter could be understood as ordinary matter seen through a different temporal direction. This was not merely a clever analogy. It was a structural identity within the theory itself. The equations did not say, "This could be thought of that way." They said, "This is the same thing." Such an idea shattered classical notions of causality. If antimatter is matter moving backward in time, then interactions are no longer simple sequences of cause followed by effect. They become spacetime events, complete structures that exist as wholes. What we call a beginning or an end is often just a matter of perspective. Feynman's brilliance was not only in recognizing this symmetry, but in using it practically. He realized that if these interpretations were mathematically identical, physicists were free to choose whichever one made calculations simpler. This freedom led to a completely new way of visualizing particle interactions. Instead of drowning in equations, one could draw pictures that encoded the math directly. These visual representations allowed physicists to see time, space, matter, and antimatter as parts of a single unified process. A particle line moving upward represented motion forward in time. The same line moving downward represented motion backward in time. Where lines met, particles interacted. What previously required pages of calculations could now be understood at a glance. This was not a simplification in the sense of cutting corners. It was a revelation of structure. The diagrams did not hide complexity, they organized it. And crucially, they made clear that time reversal was not an anomaly. It was built into the fabric of the interactions themselves. The deeper implication of Feynman's rethinking was philosophical as much as physical. It suggested that time might not be a fundamental ingredient of reality, but a derived one. At the deepest level, the universe may be described by relationships between events rather than by a flowing temporal backdrop. Past and future are labels we impose, not boundaries nature obeys. This idea aligns with one of the strangest features of quantum mechanics, the lack of a preferred temporal direction. Many quantum processes work just as well backward as forward. The laws do not break when time is reversed. What breaks is our intuition. Matter and antimatter interactions provided the perfect testing ground for this radical view. When matter and antimatter collide, they annihilate into energy. This process looks violent and final. But under Feynman's interpretation, it can be seen as a smooth continuation of particle paths through time. Nothing truly disappears. The process simply rearranges how energy and momentum flow through spacetime. This perspective removes the sense of drama and replaces it with inevitability. What appears as creation or destruction is simply transformation. The universe does not pause to consider direction. It follows consistency. The success of this reinterpretation was proven not by philosophical arguments, but by experimental accuracy. Calculations based on Feynman's framework matched experimental results to unprecedented precision. The magnetic moment of the electron, for example, was predicted with accuracy so extreme that it became one of the most precise agreements between theory and experiment ever achieved. This level of precision left no room for doubt. A theory that predicts reality to that degree cannot be an illusion. Whether or not particles really travel backward in time becomes almost irrelevant. What matters is that treating them as if they do produces correct results every time. Yet the conceptual impact remains profound. Feynman forced physicists to confront the possibility that time is not sacred. It can be reversed, reinterpreted, and rearranged without breaking the laws of nature. What breaks instead is the human need for linear storytelling. This does not mean the future causes the past in any simple way. The universe remains consistent. Paradoxes do not arise because the equations enforce strict constraints. Time symmetry does not imply chaos. It implies balance. Feynman's approach also dissolved the sharp boundary between particles and interactions. In classical thinking, particles exist first and then interact. In Feynman's view, interactions are primary. Particles are defined by how they interact across spacetime. Their identity is relational, not intrinsic. This shift had lasting consequences. It influenced how physicists think about fields, forces, and even the vacuum itself. Empty space, once thought to be nothingness, became an active participant filled with fluctuations, virtual particles, and temporary violations of classical intuition. These virtual particles, often described as popping in and out of existence, are another manifestation of time symmetry at work. Virtual particles can be thought of as particles briefly borrowing energy, appearing, interacting, and disappearing. In Feynman's framework, these processes are not violations of time or energy, but permitted fluctuations within strict limits. Time again proves flexible, not absolute. The radical nature of this thinking was initially unsettling. Many physicists resisted it, not because it failed experimentally, but because it challenged deeply held assumptions about reality. But science does not advance by comfort. It advances by coherence. Over time, Feynman's interpretation became foundational. Today, no serious work in particle physics avoids it. The language of backward time motion is embedded in how physicists calculate, visualize, and understand fundamental processes. It is no longer controversial, it is essential. Yet its implications continue to echo beyond physics. If time is not fundamental, then questions about free will, determinism, and the nature of existence take on new dimensions. The universe may not unfold moment by moment in a cosmic present. It may exist as a complete structure, with past and future equally real. This does not diminish human experience. It reframes it. We experience time sequentially because of how our brains work, not because reality demands it. The flow of time may be a feature of consciousness, not of the universe itself. Richard Feynman did not claim to have the final answer to what time truly is. What he did was strip away assumptions and reveal a deeper consistency beneath them. Matter and antimatter, once seen as opposites, became reflections across time. Time itself became a dimension to be navigated mathematically rather than a river to be obeyed. This radical rethinking did more than solve equations. It changed the language of physics. It taught scientists to trust mathematics even when it contradicts intuition, and to trust experiments above all else. It showed that reality does not owe us simplicity, only truth. In the end, Feynman's contribution was not about proving time travel in the human sense. It was about proving that time is far more subtle, flexible, and mysterious than we ever imagined. And by daring to follow that mystery wherever it led, he reshaped our understanding of the universe itself. The history of physics contains rare moments when mathematics steps ahead of experiment and points toward a truth that no instrument has yet seen. These moments are unsettling because they require scientists to trust symbols on a page over direct observation. The third keynote revolves around one of the most powerful examples of this phenomenon, how equations predicted reality long before experiments confirmed it, and how this predictive power became one of the strongest proofs that the strange ideas behind modern quantum physics were not imagination, but truth. In everyday thinking, experiments come first and theory follows. We see something happen, then we build an explanation around it. But in fundamental physics, the process often runs in reverse. Equations are not invented freely. They are constrained by deep principles such as symmetry, conservation, and consistency. When these principles are followed honestly, the resulting mathematics sometimes reveals features of reality that no one expected and no one was ready to accept. This was exactly what happened when physicists tried to describe how light and matter interact. Early quantum theory worked beautifully for atoms, but it ignored Einstein's relativity. When scientists tried to unite the two, the equations became far more demanding. They insisted on mathematical completeness, and completeness brought consequences. One of those consequences was the appearance of solutions that seemed physically impossible. The equations describing electrons interacting with light produced terms that looked like particles with negative energy or motion reversed in time. At first, these results were treated as errors or flaws. Physicists assumed that future corrections would remove them. Instead, the opposite happened. As the equations were refined, these strange features became more pronounced, not less. The mathematics was not malfunctioning. It was revealing something hidden. Long before antimatter was directly observed, the equations already contained it. They predicted particles identical in mass to electrons, but with opposite charge. They predicted that these particles would appear naturally in high-energy interactions. They even predicted how these particles would behave when encountering ordinary matter. At the time, this seemed absurd. How could equations predict an entire form of matter that no one had ever seen? Then experiments caught up. When particle accelerators reached sufficient energies, these predicted particles appeared exactly as the equations said they would. Not approximately, not vaguely, precisely. The mass, charge, and behavior matched the predictions in every measurable way. What had once been dismissed as mathematical nonsense became undeniable reality. This pattern repeated itself over and over. The equations did not just predict new particles. They predicted relationships, interaction strengths, and subtle effects that could not be explained by classical intuition. One of the most striking examples involved the behavior of electrons in magnetic fields. Classical physics predicted a certain value for the electron's magnetic moment. Early quantum theory improved this prediction slightly, but the refined equations of quantum electrodynamics predicted corrections so small that measuring them seemed almost impossible. These corrections arose from interactions involving virtual particles and time-symmetric processes that existed only within the equations themselves. Yet, when experiments were finally performed, the measured values matched the predictions to an astonishing number of decimal places. This agreement remains one of the most precise in all of science. It was not luck. It was proof that the equations were capturing something real, even when that reality defied visualization. What made this so extraordinary was that many of these predicted effects involved processes that could not be observed directly. Virtual particles backward, in time paths, and fleeting fluctuations were not things detectors could see. They were internal components of the theory, and yet their consequences were measurable. Reality behaved exactly as if these invisible processes were happening. This is where the idea of time-symmetric motion gained credibility. The equations treated forward and backward time processes on equal footing. They did not privilege one direction over the other. When calculations included both, the results matched experiments. When they did not, the theory failed. This forced physicists to confront a difficult truth. Whether or not backward time motion was real, in a philosophical sense, it was operationally real. The universe responded to calculations that assumed it. Ignoring it led to incorrect predictions. Including it led to stunning accuracy. The predictive success of the equations created a shift in scientific attitude. Instead of asking whether an idea felt reasonable, physicists began asking whether it worked. Reality became the judge, not intuition. This shift was not comfortable. It required abandoning familiar mental images. Particles were no longer tiny billiard balls. Interactions were no longer simple collisions. Instead, reality became a network of probabilities and paths, many of which contradicted everyday experience. Yet the equations did not care. They continued to produce correct answers. One of the most unsettling aspects of this predictive power was that it suggested the universe is fundamentally mathematical. The equations did not merely describe reality, they seemed to uncover it. Features like antimatter and time symmetry were not added by hand. They emerged inevitably from the structure of the theory. This raised deep philosophical questions. Is mathematics invented or discovered? If equations can predict entire classes of particles before they are observed, what does that say about the nature of reality? Are the laws of physics written into the fabric of the universe, waiting to be read? While these questions remain open, the practical implications were clear. Trusting the equations worked, doubting them did not. The predictive success also provided a kind of indirect proof of ideas that could never be tested directly. No experiment can watch a particle move backward in time. No detector can capture a virtual particle popping in and out of existence. But experiments can measure the outcomes of interactions, and those outcomes carry the fingerprints of these processes. When predictions that depend on such processes are confirmed, the processes themselves gain legitimacy. They may be unobservable, but they are not imaginary. They are necessary components of the explanation. This is how physics often advances. It accepts entities not because they can be seen, but because they must exist for the theory to work. Electrons were once unobservable. Atoms were once hypothetical. Gravitational waves were once predicted purely by mathematics. In each case, equations came first, experiments followed, and reality aligned with theory. The same pattern applies here. The strange time, symmetric features of quantum theory were not philosophical speculation. They were mathematical necessities, and their success in prediction turned them into physical truths. This success reshaped the role of theory in science. Equations became explorers, venturing into unknown territory ahead of experiments. Experiments became confirmations, following where theory led. The relationship between mathematics and reality grew more intimate. Physicists began to suspect that the universe does not merely obey mathematical laws, but is, in some sense, built from them. Time, matter, and energy became expressions of deeper symmetries rather than independent entities. This view explains why equations can predict reality so well. They are not approximations layered on top of chaos. They are reflections of the underlying order. The predictive power also demanded humility. If equations could reveal truths so far removed from human intuition, then intuition could no longer be trusted as a guide to fundamental reality. It could guide imagination, but not judgment. This realization marked a turning point. Physics stopped asking whether reality made sense and started asking whether it was consistent. Consistency replaced comfort as the highest standard. The third keynote, then, is not just about equations predicting experiments. It is about a shift in how humanity understands knowledge itself. Truth is not determined by what feels right, but by what survives contact with reality. When equations predict particles that have never been seen, and those particles later appear exactly as predicted, something profound has occurred. The universe has spoken through mathematics. In that moment, the boundary between abstraction and reality dissolves. Symbols on a page become mirrors of the cosmos, and ideas once dismissed as absurd become pillars of understanding. This is the power that turned strange equations into accepted truths, and transformed speculative mathematics into one of the most reliable descriptions of reality ever created. When a single idea forces an entire field to change its direction, its influence cannot be measured only by awards or citations. It must be measured by how deeply it reshapes understanding, tools, and questions for generations to come. The fourth keynote centers on why this strange interpretation of time, matter, and antimatter did not remain a curiosity, but instead transformed modern physics at its core, redefining how scientists think about the universe itself. Before this shift, physics was fragmented. Different theories explained different phenomena, but they often spoke different languages. Classical mechanics worked for large objects. Quantum mechanics worked for atoms. Relativity governed high speeds and strong gravity. The challenge was not just to make these theories work, but to make them coherent. The reinterpretation of time and antimatter became one of the bridges that allowed this coherence to emerge. The most immediate transformation occurred in how physicists approached calculations. Prior to this conceptual breakthrough, attempts to calculate how light interacts with matter often produced infinite results. These infinities were not minor errors. They rendered the theory useless. A calculation that predicts infinite energy or infinite probability cannot describe reality. Physicists were stuck. The equations looked correct in principle, but they failed in practice. The reinterpretation of particle behavior across time allowed these infinities to be reorganized and controlled. Instead of treating problematic terms as meaningless, physicists learned how to combine them in ways that canceled out unphysical results. What once looked like chaos resolved into structure. This was not a mathematical trick. It reflected a deeper understanding of how interactions unfold in spacetime. This breakthrough turned quantum electrodynamics into a predictive and reliable theory. For the first time, physicists could calculate complex interactions involving multiple particles and forces with confidence. This success set a standard. Any new theory would now be judged by whether it could match this level of precision and consistency. The impact did not stop with electromagnetism. The same conceptual framework spread to other forces of nature. The strong nuclear force, responsible for holding atomic nuclei together, was described using similar principles. The weak force, responsible for radioactive decay, adopted the same language. What began as a solution to one problem became a universal approach. This unification was possible because the reinterpretation revealed a deeper symmetry in nature. Time reversal symmetry, charge symmetry, and parity symmetry became central organizing principles. Instead of treating matter and antimatter as fundamentally different, physicists learned to see them as related by transformations. This shift simplified theories while making them more powerful. Modern particle physics is built on these symmetries. The Standard Model, which describes all known fundamental particles and forces except gravity, relies heavily on the ideas that emerged from this transformation. Without them, the model would collapse under its own complexity. Another profound impact was on how physicists think about interactions themselves. In classical physics, interactions happen at specific moments in time. A force is applied, an effect follows. In the modern view shaped by this idea, interactions are extended processes in spacetime. They are not isolated events, but interconnected histories. This perspective changes the meaning of cause and effect. Rather than a simple chain,